Now our more focus is specifically a property of unit ball in d-dimensional space. In the previous lecture, we have seen that the volume is concentrated with the small annulus with the width big O of 1 by d near its boundary. Next, what we are going to discuss is what will happen in d-dimensional space, what will be the volume of a unit ball, and what is your prediction that if d tends to d tends to infinity, what should happen to the volume of d-dimensional unit ball? What is your guess? What you will say? What should happen to volume of a unit ball in d-dimensional space? Suppose if d is tending to infinity, what should happen to the volume of unit ball? Where it should tend? What is your answer? Yes, guys? Any guess you can? So, as per the discussion which we are going to discuss today is if d is tending to infinity, then the volume of unit ball will tends to 0. These things will prove later on in this lecture. So as we have discussed in my previous lecture, to calculate the volume, we denoted by volume of this unit ball, we have denoted that is by Vd in d-dimensional space. And one can investigate the volume using the Cartesian coordinates or using polar coordinates. In the Cartesian coordinates, which we have discussed in previous lecture, that in Cartesian coordinates, the volume is given by Vd is equal to, as we have discussed, that x1 running from -1 to 1, x2 running from square root of -1 minus x1 square to plus 1 minus x1 square. X3 is square root of minus of 1 minus x1 square minus x2 square to plus 1 minus x1 square minus x2 square up to so on. The last one is xd, it is minus of 1 minus x1 square x2 square up to xd minus 1 square up to 1 minus x1 square minus x2 square up to minus of dx minus 1 square, and the integration is over x d xd minus 1 up to xd1. So this is the volume of unit ball in Cartesian coordinates we have discussed in previous lecture. Also, we have investigated using the polar coordinates, and it is easy to investigate or calculate. So it is easier to investigate using polar coordinates. In polar coordinates, The Vd is given by, Vd is nothing but the volume of d-dimensional unit ball. As we have discussed, it is the surface area into certain things. So that is Vd, we have already discussed this one, that is SD, the integration running from R running from 0 to 1, R d power 1 dr d omega, where this integration, where this omega and r are the variables and do not interact each other, that means they are independent variables. Since the variable omega and r do not interact, this Vd can be written as integration Sd d omega integration r running from 0 to 1 r raised to d minus 1 dr. So if you take the integration of this term, that is Sd d omega r power d upon d, and the limit is from 0 to 1. You substitute 1 here, that will gives me 1 upon d. When you substitute 0 here, it will be 0. So finally you will have 1 upon d integration Sd d omega. And what is this? This quantity is exactly the surface area of d-dimensional unit ball, that I am denoting by AD upon d. So where AD is the surface area of d-dimensional unit ball. For example, if d equal to 3, d equal to 3 means we are talking in the three-dimensional unit ball, that is a sphere in R3. What will be the volume of a sphere? We know that it is 4 by 3 pi
4
r
by 3 pi r cube.
cube. So, but r is 1 because we have taken a unit sphere, so it is 4 by 3 pi. And what is the surface area of sphere? The surface area of the sphere is 4 pi r square, 4 pi r square. But r is 1 here, so that's why it is 4 pi. And you just see that the previously we have formula, that is Vd is equal to AD upon 3, sorry, d. Here d is 3, so it will satisfy this formula, that you can say that this is the AD, that I can say A3, and this is V3. So we have already V3 is equal to AD upon 3. So it's satisfying this, what we have achieved for d-dimensional unit ball. Now to calculate this Vd, it is remain to calculate what is this AD. That means what will be the surface area of the unit ball. For in general, NED is given to us. So now our objective is to calculate what is this value of AD, and that is slightly different way we are approaching in a different manner to achieve this AD. So that will write. The question remains, how to determine the surface area AD, that is integration SD d omega, or in general d. So to do this one, we'll slightly go off track and then come back to this problem. So for that, I'm considering this different integral. So that I'm denoting by id. That is minus infinity to infinity, minus infinity to infinity, up to so on minus infinity to infinity, e power minus x1 square plus x2 square up to xd square, xd, xd minus 1 up to xd2 dx1. So I'll consider this integral. Now including the exponential here, allowed to integrate from minus infinity to infinity, stopping the surface of the sphere. And this id can be computed by interacting both Cartesian and the polar coordinates. So we'll use to compute this id, we'll use the Cartesian coordinates as well as polar coordinates. Integrating in polar coordinates, this id is exactly the surface area AD. That will prove that later on. And equating these two results is allowed to solve this AD. So what is our objective is to calculate this ID. And in polar coordinates, this ID is exactly the surface area. And in Cartesian coordinates, we evaluate this one. And then we can have a results in, or we can have the formula for AD. So first let us calculate what is this ID by integrating it into the Cartesian coordinates. So we know that this ID, we can write down this is as minus infinity to infinity. This will be minus infinity to infinity up to minus infinity to infinity e power minus x1 square into e power minus x2 square up to into e power minus xd square dxd up to dx2 x1. We can write this from this one. It's a simple property of exponential function, that is e power x plus y. I can write down as e power x into e power y. Using this property of exponential function, we'll be able to write down this form. Now this is independent of other variables other than x1. This is independent other than x2. So this integration I can write down in this form: minus infinity to infinity e power minus x1 square dx1, integration from minus infinity to infinity d minus x2 square dx2 up to so on, integration from this to this e power minus xd square dxd. This we can write. Now the question is, what will be the integration of this one? So those who have done their course of advanced calculus, they probably learn what will be this integral is. If not, then I can try to prove this one. But before that, you should know some knowledge of a gamma function. So anyone know what is a gamma function? Yes. Anyone from you guys know that what is the gamma function? No one know what is gamma function? Okay, no problem. So now question is to evaluate this integral. Minus infinity to infinity e power minus x square dx. This is our objective, because That is the involve this quantity. Each and every component of this one will gives me this. The ultimate goal is to achieve this one, and my objective is to prove that this is square root of pi. This is my claim. This integral is a square root of pi. So I will do this way. I make copy of this two, that is minus infinity to infinity e power minus x square dx square. That I can write down minus infinity to infinity e power minus x square into e power minus y square dx dy. Because it is a square, so I can write down multiplication this to quantity. This is actually a double integration, minus infinity to infinity, double time integration is there. So this will gives me minus infinity to infinity e power minus x square plus y square dx dy. Now to calculate this one, we'll convert this into the polar coordinates. Let us substitute, put x is equal to r cos theta and y equal to r sin theta. If you substitute this one, then you will have x square plus y square is equal to r square. And what is your r is moving here? R and theta. So what is this? X is minus infinity to plus infinity, y is also minus infinity to plus infinity. So we can see that its entire plane is covered by this limit. So that's why your limit of r and theta should be covered by entire plane. So what is your r? Value of r is this, that is the distance from origin to any plane. So that is r is 0 to infinity. And since you want to cover entire plane, your theta is running from 0 to 2 pi. So these are the limits of r and theta you will have. If you convert this is in terms of polar coordinates. And dx dy as per the Jacobian, it is the mode of j dr d theta. And this mode of j is nothing but the r dr d theta. So converting into the polar coordinates. And what is this Jacobian? That is Jacobian of r theta with respect to, that is the Jacobian of xy with respect to r theta. This is j, that will be the del x by del r, del x by del theta, del y by del r, del y by del theta. As you know, x is r cos theta, y is r sin theta, and del x by del r is cos theta. Del x by del theta is minus r sin theta. Del y by del r is r sin theta, so that is the derivative of is sin theta, and the derivative of this with respect to theta will gives you r cos theta. So that will gives me r cos square theta plus r sin square theta. So the finally you will have r, because cos square plus sin square is 1. So that is the mode z, that is r dr d theta. So now this integral, I will say this integral is, let's say, I. So next what we get, it is double integration minus infinity to infinity e power minus x square plus y square dx dy will change to r running from 0 to infinity, theta running from 0 to 2 pi, e power minus r square r dr dt. Now to take the integration of this one, you just see that it is of the form e power fx into f dash x dx, the derivative. So I'll just multiply and divide by 2 here, minus 2r, 1 by 2. So that is theta is running from 0 to 2 pi, integration r running from 0 to infinity, e power minus r square, and here I'll just set minus 2r. R is already there, so I'll just multiply and divide by minus 2 here, dr d theta. So it is of this form, where fx is this, r square, and f dash the derivative of this r square minus r square, that is minus 2r. So here if you just take the fx is equal to t, then f dash x dx is equal to dt, will leads to this is e power t dt. So integration of e power t is e power t. What will be the integration of this quantity? It is minus 1 by 2, theta is from 0 to 2 pi, e power, what will be this? Minus r square, because the value of t is fx, which we have to substitute again, and the limit is from 0 to infinitive d theta. When you substitute infinitive here, what will be the answer?
0.
0. Why? Because it is e power minus infinity. E power minus infinity is 1 upon infinity. 1 upon infinity is 0. So 0 minus, when you substitute 0 here, e power 0 is there, which will be 1. So you will have 1 d theta. So it is the integration, this minus minus become plus. So finally you will have this double integration, or I can say infinitive minus e power minus x square dx whole square, because this integration we have conclude from the square of this thing. So that's why square of this thing will be 1 by 2, 0 to 2 pi d theta, because this minus minus become plus, and the integration of theta d theta is just theta, so that's why it is 1 by 2 pi is minus 0, so that will equal to pi. So hence the finally you will have this is square root of pi. This is our objective to prove. Okay, so we'll come back to this question again, that is what is id. So this is a square root of pi as per the argument which we have proved here. So therefore what we can say that id will be square root of pi into square root of pi up to so on square root of pi d times. So this is nothing but the pi raised to d by 2. This is the value of this id that we got. Okay, next we need to calculate interchanging this id into the polar coordinates. Okay, now we need to do this into the polar coordinate. Now what we have, now what we'll do is now calculate id by interchanging in polar coordinates. So we have to change into the polar coordinates the volume of the different element differential element, that is r raised to d minus 1 d omega dr. Thus, that is the Jacobian that we have, did it here by converting dx dy in terms of r dr d theta. So that is Jacobian we have calculated. Here for d dimension, we just assume that is this thing, r raised to d minus 1 d omega dr. So now this integration id that we have in this form, minus infinity to infinity, minus infinity to infinity, up to minus infinity to infinity, e power minus x1 square, x2 square, up to xd square, dxd up to dx2, dx1. This is our id. We'll need to convert this one into polar coordinates. So that means what will be the value of x1 square plus x2 square up to xd square? that value is r square, and this dx1 or dxd dx2 d minus 1 up to dx2 dx1 is nothing but the r raised to d minus 1 dr d omega, where this omega is a integral or surface integral that we have. So this integral in polar coordinates will change to, that is, integration sd integration r running from 0 to infinity e power minus r square that we have already, and this quantity is changed to this one into the polar coordinate, that is r raised to d minus 1 dr d omega. Now this r raised to this, both omega and r independent variables, so that's why, and they do not interact with each other. So this id we can have, that is integration sd d omega integration r running from 0 to infinity r raised to d minus 1 dr e power minus r square is also there, that is this. And now this is what we have, this one we have denoted in the previously also, this is AD, that is the surface area. And how to integrate this one? So that integration involves the use of gamma function. Okay, so that I'll write, for now it is as it is. And let us recall what is gamma function, which you have did it on in your advanced calculus course. So gamma function is gamma n, denoted as this gamma n. What is the value of gamma n? It is e integration from 0 to infinity e power minus t power n minus 1 dt. This is the gamma function. For n greater than 0, this is defined. What we have here is integration 0 to infinity e power minus r square d power r power d minus 1 dr. This is the quantity we have. We need to integrate this one using this gamma function. So just observe that what is the comparison you can do. Instead of t we have r square, so just substitute r square is equal to t. If I can say this is L, so if I can say this is r square is t, so 2r dr is equal to dt. So that means the dr, value of dr is 1 by 2. The value of r that we say, it is t raised to 1 by 2. So it is t raised to minus 1 by 2 dt. So this value of L we got, and if r is 0, t is 0, and if r is infinity, t is also infinity. That we can easily see from this r square is equal to t. So hence what we get, it is L is 0 to infinity e power minus t, then it is r power d minus 1, but the value of r is t power 1 by 2 and whole power d minus 1. So that will leads to d minus 1 by 2 into dr is there. A dr, value of dr is this 1 by 2 t power minus 1 by 2 dt. If you simplify this one, then this is 0 to infinity e power minus t power 1 by 2, I'll take common out. This is d minus 1 by 2 minus 1 by 2 dt. If you simplify this one, this is 1 by 2, 0 to infinity e power minus t power d by 2 minus 1, because 1 by 2 minus 1 by 2 will be minus 1 dt. And if you compare this integral with the previous, the gamma function that we have here, just see that e power minus t is there. T power n minus 1, instead of n we have here, it is 1 by d by 2. So this is what? This is 1 by 2. It is already there, gamma d by 2. So this, the value of this integral that we have here, it is gamma 1 by 2. So from this equation 1, what we can obtain, id equal to ad into gamma d by 2 into 1 by 2, because that is the value, 1 by 2 into gamma d by 2. We'll substitute that value here. So from this and the value of AD we have already calculated. So therefore AD equal to 2 into 1 upon gamma d by 2 into ID. And the value of ID we already calculated. The value of ID we have calculated previously, that is here. If we can say this is equation number star, then from star we can have this value, that ID is equal to pi raised to d by 2. This is because of star. So that means we have the surface area is this. Okay, so this is the formula for surface area we got. So hence the surface area is AD equal to 2 into pi raised to d by 2 upon gamma d by 2. Therefore now volume VD, as you have seen previously, what will be the value of, what is the relation between this VD and AD? The relation of VD and AD is this, that we have discussed here. That is VD equal to AD upon D. I will say this is a double star. So from this double star, what we got, AD upon D is this. Now value of AD we have already this. So we'll have now VD, that is 2 into pi raised to d by 2 upon t into gamma d by 2. And you can, this is the formula for AD and this is the formula for VD. So what we can write a statement here is, the statement we can write is this: the surface area AD and the volume VD of unit radius ball in d-dimensional space are given by AD equal to 2 pi raised to d by 2 upon gamma d by 2 into VD, that means, and VD equal to 2 by d pi raised to d by 2 into gamma d by 2. And you can check, verify, if you want, you can just verify that the formula for V2, what will be the V2? That means D equal to 2. Here, if I put D equal to 2, this 2 will cancel out. Pi raised to 2 by 2, so it is gives me pi. This will gives me D is 1, so gamma 1 by 2. Gamma 1 by 2 is, what is the gamma? 2 by 2, gamma 1. Gamma 1 is 1.
1.
Yeah. So that means this is gives me pi. For V3, you just verify with your. So for V3, what we have here, it is 2 by 3. This is 2 by 3. Pi raised to 3 by 2 upon gamma D. D is 3, so it is 3 by 2. Now what is the gamma 3 by 2? Gamma n. We know it is n into gamma n minus
N
1.
minus 1.
So it is 3 by 2. We can write down as 1 by 2 into gamma 1 by 2. And gamma 1 by 2, we know it is root pi. Okay, so this is 2 by 3 into pi raised to 3 by 2 into 1 by 2 into pi raised to 1 by 2. Gamma 1 by 2. Root pi is 1 by 2. This 2 will get cancelled out. Sorry, not cancelled. This is denominator, so it goes in the numerator. 2, 1 by 2. So that is 4 by 3, and this 1 by 2 will get cancelled out and left with only pi. So it is 4 by 3 pi. That is the volume for the surface area. Similar manner, you can check for the surface area. And now, what I have told you, that what will happen if D is tending to 0, sorry, infinity. So in the numerator, let me take this quantity on the other. So Vd we have here, that is 2 by D, pi raised to D by 2, gamma D by 2. This is the value we have. What is the limit D tends to infinity Vd? What will be this? And this will tends to 0, because in the numerator you have a exponential function. That means pi raised to D by 2, exponential in D by 2. And in the denominator you have a gamma 1 by 2. And gamma is a generalization of a factorial. So it is kind of factorial D by 2. So which one is going fast? Factorial is increasing fast or exponential will increase fast? Definitely the factorial will increase fast. So this denominator is, if the value of D is higher, then this denominator goes to infinitive, more faster than the numerator. So that's why this will tends to 0. So here what we have derived, that in higher dimensional space, a volume goes to 0. A volume or a mass you can consider as a mass which will goes to 0. Okay, so that is the things. If you have any question, you can ask regarding this.